So here are the answers to the questions at the end of the previous chapter. Hopefully you've got all these right. So why don't you tick these off before we go on to the extraction of metals. So let's have a look at how we obtain metals from ores. Now the definition of an ore is a rock which contains enough of a metal to make it economically worthwhile to extract the metal. Now these economics may change over time, so for example if the price of the metal goes up or if the processing becomes cheaper, then previously uneconomic ores may now be exploited. It may be worth your while. Now ores are mined. This involves again clearing land and digging up and processing large amounts of rock, which has a huge environmental impact. Most metals are found as compounds, which then require chemical reactions to extract the metal itself, and it's only very unreactive metals, such as gold, which are found in their pure form as pure metal. Reactivity series. Now some metals are more reactive than others, and they can be put in order of reactivity, so most reactive at the top and least reactive at the bottom. More reactive metals will displace less reactive metals from compounds. For example, zinc will displace tin from tin oxide, forming zinc oxide and tin. Now carbon has a role here. It's not a metal, but it can also be used to displace metals which are lower down the reactivity series than carbon. For example, we can heat iron oxide with carbon. Carbon displaces the iron, forming iron and carbon dioxide. So here is the reactivity series of metals. You don't need to learn this because this comes on your data sheet. You'll see we've got the most reactive metals at the top, so potassium is the most reactive metal. Platinum is the least reactive metal. Carbon and hydrogen are non-metals, but nevertheless they're placed in order of their reactivity. So any metal can displace anything below it in the reactivity series. Carbon can displace any metals below it, and hydrogen can displace any metals below it. So how do we extract iron from iron ore? Now, iron is found in iron ore, in the rock, as iron oxide. So we have to remove the oxygen. Remember, this is called reduction. So for the oxygen to be removed, for the iron oxide to be reduced, iron is heated with carbon in a huge piece of kit called the blast furnace. Now, carbon is more reactive than iron, so it displaces the iron and takes away the oxygen. So carbon dioxide and iron are formed. So here's the word equation. Iron oxide plus carbon forms carbon dioxide plus iron. Any metal that's less reactive than carbon can also be reduced in this way. So let's have a look at how copper is extracted. It's a different process. Copper can be extracted from ores by smelting. This is roasting in a furnace. The copper ore may contain sulphur impurities, so when these are heated with air, sulphur dioxide may be given off as a waste gas, and it's strongly acidic, so it has to be scrubbed from the waste gases. The copper then may need to be purified using electricity, and the smelting and the electrolysis use a huge amount of energy, so this makes it a very expensive process and creates a large environmental impact. The problem is that copper ores are running low, so we're needing to look at extracting copper from lower grade ores. Now what lower grade ores means is rocks which contain rather a low amount of copper, previously uneconomic. Now these new methods use less energy, they don't destroy the environment in the same way, and phytomining has the advantage that using plants absorbs carbon dioxide as they grow, and it then releases energy when they're burnt. So let's have a look at phytomining. Now in exam questions about this. It's not good enough just to write about the new methods without naming them. You have to name them. You have to say phytomining and bioleaching. So in phytomining, we grow plants on the low-grade ores, and the plants absorb the copper through their roots, and the copper becomes part of the plant material. The plants are then burnt, and the copper is extracted from their ashes using sulfuric acid. So we end up with a solution of copper ions in the form of copper sulphate. Bioleaching uses bacteria which grow and feed on the low-grade ores, and then once the bacteria have been processed, again we end up with a solution of copper ions in the form of copper sulphate solution at the end. So with both these methods the end product is copper sulphate solution. So we've then got to extract the copper from the copper sulphate solution. Now both these processes result in a solution of copper sulphate. So we need to then get the copper metal from the copper sulphate solution. So there's two ways of doing that. Either scrap iron is placed in the solution. Now iron is more reactive than copper, so iron displaces copper from copper sulphate. So we end up with iron sulphate and copper metal. Or we can extract the copper by electrolysis. Now this is using electrical energy to separate the ions. So we pass an electrical current through the copper sulphate solution. We have electrodes in the solution. We have a positive and a negative electrode. Metal ions are positive. Now opposites attract. The positive metal ions are attracted towards the negative electrode. So copper metal is deposited on the negative electrode. Both these methods, the disadvantage is that only a small amount is extracted and the processes are not continuous, so it's quite a slow rate of production. So how do we extract aluminium and titanium? Now, aluminium is more reactive than carbon, so it can't be extracted by reduction with carbon in the same way that iron can. Aluminium must therefore be extracted by firstly melting the ore and then passing an electric current through it, so the positive aluminium ions move to the negative electrode. But there's so much expensive energy used in this process, firstly to melt the ore and then to electrolyse it. This makes aluminium a very expensive metal. Titanium reacts with carbon itself. So again, titanium can't be extracted by reduction with carbon either. Titanium has to be extracted by displacement with something even more reactive, and we use sodium or magnesium for this. But these are expensive to extract also. So all these many steps that are involved in extracting titanium and aluminium make both of them expensive metals. Okay, so quickly test yourself. Hopefully you've printed out all these notes so you can answer it now and find the answers at the beginning of the next chapter.